This is the lecture for Module 9 in the book Problem-Solving Guide for Electromagnetism and Optics, Magnetic Induction. This module has one main concept. A changing magnetic flux through a loop produces a voltage in that loop whose magnitude is the rate of change of that magnetic flux. We put the voltage in quotes here because voltage is usually reserved for batteries. So we use the term EMF, electromotive force, but it does the same thing as a battery. It pushes a current around the loop. The units of the EMF are volts, and you can use EMF equals IR just like you would use V equals IR. So you think about EMF as a voltage that drives a current. In language of mathematics, we can write the EMF in a loop is the negative rate of change of the magnetic flux. And the magnetic flux is B times A. It's a dot product of the vector B and A. Usually B and A are parallel. Usually the current is going, the B field is going directly through the loop. The magnitude of the magnetic flux is BA cosine theta. Theta is the angle between B and A. Usually that angle is 0. When the magnetic field is going directly through the loop, the angle 0, cosine of 0 is 1. The magnetic flux is B times A. So for example, we have a magnetic field B coming directly out of the page. We have a circular current loop, a circular loop in the field. The flux through the loop is B times A. If that flux isn't changing, there will be no current in the loop. If the flux changes for one reason or another, there will be a current generated in the loop. The magnetic flux is 0 when the field lines are not penetrating the loop. Here the field lines are to the right. The area vector is out of the page. The angle between B and A is 90 degrees. Cosine of 90 degrees is 0. But obviously, if you look at it, the field lines are not going through the loop, so the magnetic flux is 0. The EMF created in the loop has nothing to do with the magnitude of the magnetic flux, only to do with its rate of change. Rate of change. How quickly is the flux changing? It's similar to the relationship between speed and linear acceleration. Doesn't matter how fast you're going in a straight line, if your speed's not changing, your acceleration is 0. The magnetic flux can be huge, but if it's not changing, there's no EMF in the loop. It's d phi dt, the rate of change of the flux. If it's not changing, there is no EMF, there is no voltage, there will be no current. First, let's address the negative sign to get that direction. Then we'll address the magnitude. The negative sign indicates the EMF produces a voltage that will drive a current opposite to the change in the magnetic flux. It'll drive a current to produce a flux that opposes the change in the flux. So let's consider a rectangular wire partially in a magnetic field. L is the length of the wire loop in the field. It's not the whole length. All of the width is in the field, so that's W. The loop has a flux equal to B times A. The magnitude of this field in this area, W times L, the area of the loop that's in the field, that's the magnetic flux. It's B times A, which is also B times W times L. Now we're going to change the flux through the loop. And we can do that by pulling the loop downward. If we pull it out of the field, the flux is going to change. In fact, it's going to go down. Since the flux is changing, there's going to be a current in that loop. There's no battery there. It's an electromotive force produced because the flux is changing. The current in the loop will produce a flux through the loop that opposes the change in flux through the loop. Everything is through the loop. We don't care what's going on outside the loop. When the loop is pulled out of the field, the flux through the loop is decreasing, so the current in the loop will produce a flux through the loop that adds to the flux. It doesn't want to change. If it's losing flux, it's going to add flux. So now the question is, which way does the current have to go to produce a magnetic flux through the loop out of the page? It's got to be counterclockwise. If you stick your thumb up on the right-hand vertical part, it'll produce a magnetic field out of the page. So it's counterclockwise all the way around. We can put arrows all the way around counterclockwise. If you're on the top, you stick your thumb to the left, your fingers point outward in the loop. If you put your thumb down on the left side of the loop, your fingers will curl around outward in the loop. So the direction of the current is counterclockwise. If I push that loop into the field, it's going to be adding flux, and the current will be produced to oppose the change. So now it's going to produce a flux into the page. And the way to do that is with a clockwise current. That's how you get the direction of the induced current. It produces a flux through the loop that opposes the change in the magnetic flux through the loop. Now let's focus on the magnitude of the voltage generated. The magnitude is the rate of change of the flux. If you pull out the loop slowly, the voltage will be low, the current will be low. If you jerk it out fast, the rate of change of the flux through the loop is high, the EMF will be high, the current will be high. So let's consider this loop shown to the left. If we pull it out at a speed V, what is the voltage generated in the loop that drives the current? We're going to pull it out at speed V. Let's get an expression. We know that the EMF is the rate of change of the flux. We already took care of the negative sign. We're looking at the magnitude. So the magnitude of EMF is the rate of change of B times A. How quickly is B times A changing? This is really the meat of the module. In almost every problem you do, you're going to say, how quickly is the product B times A changing? How quickly is the magnetic flux through the loop changing? The flux is B times A. B's not changing at all. The external B field is stationary. It's constant. We can pull out B. The reason why there's an EMF is because the area of the loop in the field is changing. So we can just multiply B by the rate of change of the area in the loop. We can also look at the area as width times length. The width of the loop that's in the field is not changing. So we can take that out. It's the length of the loop in the field that's changing. So if we pull out the W, here we have B times W times dl dt. The length, the rate of change of the length of the loop in the field. But that's just the speed of the loop, the rate of change of the length of the loop in the field. So the EMF is just B, the magnetic field, which is constant, W times the width of the loop, which is constant, times V, which is the speed at which it's being pulled out. When the loop is partially in the field, as it is in this case, there's going to be a force on the loop due to the change in magnetic flux, and we can calculate this force. Here's our diagram again. We have electric current. Electric current is moving electric charges, and moving electric charges will feel a force in a magnetic field. In our example, we pulled the loop out of the field downward, and we saw that this introduces a counterclockwise current in the loop. So the current right here is going upwards, then it's going to the left in the top, it's going downward in the section to the right, and it's going to the right, the section to the left, and the current's going to the right in the bottom section. Up, over like that. The right side has an upward current, but that's the current I. The conventional current, the electrons are moving downward. So now we have a velocity that's downward, and the magnetic field is out of the page. We put our thumb of our right hand downward. Fingers of our right hand are pointed out of the page. Our palm faces to the left. That's the direction of V cross B. But the moving charge Q, those are electrons. They're negative. We have to flip that direction, so the force will be to the right. So this part of the wire, the right side of the wire, is going to be pushed to the right. There's a force on it to the right. The magnitude is QVB. We usually use little q when we have a charge moving by itself, but here we have a whole bunch of charges in a wire. This is the force on the wire. This is not a force on an electron moving in a magnetic field. This V is the drift speed. Q is all the charge in the wire that's contributing to the current, and that's in the field. And from a previous module, this is the drift speed, I over N A Q. We can use that. Q is the charge on a single electron here. Remember that. To get the force on the wire, we need the total charge on all the free electrons in that length L. So we can just use this. The total number of electrons is the number density. This is little n is the number per volume. We've calculated that many times. Electrons per cc, or electrons per cubic meter, or electrons per gallon, if you like, times the volume. Number per volume times volume gives you the number. And it's a wire, so we have the cross-sectional area of the wire times the length of the wire that's in the field. The total charge is simply capital N times Q. The total charge on all the electrons is the number of electrons times the charge on one electron. So now we can write this. The force is QVB. That's the total charge. For the total charge, we put in N little q. And for the drift speed, we put in I over NAQ. And now we have a new expression. Now we can substitute in the number of electrons is the number density times the volume. And we have this, but it reduces very nicely. Little n's cancel, a's cancel, q's cancel. And we get ILB. Remember, L is not the length of the wire, it's the length of the wire in the field. There's wire down here, but it's not in the field, so it doesn't experience a force. Okay, now let's consider the other side of the wire. On the left, the current is counterclockwise, but this current I is downward, which means the electrons are moving upward. So we put our thumb along V, which is upward, and the B field is out of the page. Our palm is facing to the right. Electrons are negative. The force is to the left. So we saw earlier that the force on this vertical right side is to the right. The force on the vertical left side is to the left, pulling them both outward. So the net force on the loop horizontally is 0. The right side of the loop gets pushed to the right. The left side gets pushed to the left. Now let's consider this top horizontal section. I, the current, it's counterclockwise, so it's moving to the left, which means the electrons are moving to the right. V is to the right. B is out of the page. We put our thumb to the right, fingers along B. Our palm is facing downward, but those are electrons that are moving, so the force is upward. And this should make sense. The bottom part of the horizontal loop is not in the magnetic field. It's not going to experience a force. So the net force on the loop is upwards because the top part, the force on the top part is upwards. The force on the sides cancel out. The force on the bottom horizontal section is 0. This is consistent with the fact that a loop resists a change in magnetic flux. If you try to pull it out of the field, it'll exert a force upwards. If you try to push it into the field, it'll produce a force downwards. It always resists the change. This principle is used in the braking of roller coasters. When magnets are moved rapidly across conductors or vice versa, a force opposing the motion is generated. It always opposes the motion, so it's a good way to brake. This is the top thrill dragster at Cedar Point. You can see these aluminum flanges. There's magnets, strong magnets, on the roller coaster itself. And when the roller coaster, these magnets can be raised and lowered. When they go over these magnets, a tremendous braking force is applied. And you know this if you've ever been on this ride. And if you're watching this ride, if you're watching the braking, so much heat is generated in these flanges, you can see the hot air rising off of them after the roller coaster goes by. In the previous example, we demonstrated a change in flux due to the change in the area of the loop in the field. You can also change the flux by changing the field itself. Let's keep the loop stationary and change the field. Let's make the B field a function of time. Let's consider a stationary loop that's got an area of 100 square centimeters in a field that has a function of 200 millitesla minus 10 millitesla per second t, where t is the time. So there's our current loop. The B field is out of the page at t equals 0, 200 millitesla, and then it shrinks. The question is, what's the EMF in the loop? Positive is out of the page. The field starts at 200 millitesla out of the page, drops at a rate of 10 millitesla per second. At 1 second, it's 190 millitesla out of the page. At 2 seconds, it's 180 millitesla out of the page, etc., etc. Let's start by getting the direction of the induced current. You can imagine these B field lines as coming out of the page and shrinking. The B field stalks are shrinking. The current in the loop is going to be generated to add to those stalks because the flux is going down and it doesn't like any change. If the current in the loop is counterclockwise, if you put your thumb on the right side and go up, which is counterclockwise for the current, and curl your fingers around the wire, they are coming out of the page inside the loop. So the field lines are shrinking. The current in the loop is going to create a magnetic field to add to them when that's counterclockwise. So let's put a little arrow there indicating that the current is counterclockwise. Now let's focus on the magnitude. How big is the voltage that drives that current? This is related to the rate of change of the B field because A is constant. So here's the B field. There's the equation. 200 millitesla minus 10 millitesla per second T. Can you picture a plot of this? What does it look like? Do you know how quickly the B field is changing? Because that's the key. Focus on the rate of change of the B field. There's our current loop in a changing B field. There's the equation. The only thing that matters is the rate of change of the field. This 200 millitesla is a complete red herring. It doesn't matter. If it was 2000 millitesla instead of 200, the EMF is the same, because the EMF is only how quickly it's changing, not how big it is. If this constant in front was minus 500, the EMF would be exactly the same. It's only how quickly it's changing. As always, the magnitude of the EMF is the rate of change of the magnetic flux, and the magnetic flux is B times A. How quickly is the product B times A changing? That's the key. Here, A is constant. The loop is just sitting there. We can pull it out of the rate term, and we only need dB dt. And don't forget to multiply by A. So the rate of change of the field is 10 millitesla per second. It says right here, it's the thing in front of the T. So we just plug that in, and we convert the area from square centimeters to square meters, because we want to get volts. And the EMF is 1/10,000th of a volt, and it drives the current counterclockwise. If we do the resistance of the wire, we can calculate the current. There's one concept in this module. The EMF, the voltage in a wire, is the rate of change of the magnetic flux. The magnetic flux is B times A. It's usually a tough one for students because it involves a rate of change. It doesn't matter how big B times A is. What matters is the rate at which B times A is changing. We're not going to change B and A simultaneously. It's certainly possible in the real world. In this class, we're either going to change B or A. It's a good idea to figure out which one of those is changing before you start plugging stuff into equations. Finally, let's look at a couple of interesting examples of magnetic induction. If we rotate a current loop in a magnetic field, if you rotate the loop, the cross-sectional area of the loop that's perpendicular to the field is going to be changing, and you're going to get an AC current in that loop. Rotating magnets around a stationary coil will do the same thing. This is what happens in your car's alternator. So here's a blow-up view of an alternator. This is the rotor. There's magnets on this rotor, permanent magnets attached to the rotor. This spins around. Thus, the magnetic field is changing in the stationary or stator. There's a bunch of copper loops here, copper wire loops. And when you rotate the magnets in the copper loops, you get an AC current in the copper loop. And this whole thing is driven by a belt that goes to the engine. So the engine turns the magnets, and the magnets make a current in the copper loops. Another is the rail gun. A rail gun is a combination of the two things we discussed, changing B and changing A. Here we pulled the rectangular loop out of the field to create a change in flux by changing the area. Here we shrunk the magnetic field lines. We changed the magnitude of the magnetic field, did not alter the area of the loop that's in the field. We've seen that pulling downward on this rectangular loop creates an upward force without changing the field. Here we change the field. This induced a current in the wire. What if we rapidly jacked up the magnitude of the field here? What would happen to the loop? If you increase the field rapidly, the loop will move to avoid the change, and it's going to get shot out of the field. There's going to be a big force on this bar due to the induced current, and it's going to push it down. This is the basic principle of the railgun. Basic principle. It's a lot more complicated than that. Railguns developed by the U.S. Navy, they have currents that peak in the millions of amp range. So they store a bunch of charge on a capacitor and slam it through. And of course, it's not a wire because the current is so high. It's a huge rail. These two white long pieces are the rail, and these pieces are stationary. And here's the top of the loop. And this loop slides. It's called an armature. And it slides up. The force on this projectile is basically ILB. Now, B is not constant here because B, the magnetic field, is being created by the current. So when you slam 1,000,000 amps down this bar, it creates magnetic field lines. If you put your thumb along the conventional current I, it's going upward in between the rails. Then the current comes across the armature, then it goes down the other rail. In all cases, the magnetic field through this loop is upward. And it's increasing tremendously rapidly, and that shoots the armature out the front end. The magnetic field in here depends on the current as well. It's created by the current. So the force is proportional to I squared, so the bigger you make that current, the bigger the force on the projectile, which is why there's so much current in there. These projectiles have so much kinetic energy that they don't carry explosives. And you don't need any explosives to shoot them. So storing the missiles is completely safe. You don't have any gunpowder on them to shoot them, and you don't have any explosives on them when they impact their target. There's two major technological hurdles that have not been solved. One is the high power needed to make these currents. If you're on a battleship, you have to shift the power of the engines to the generators to generate this current. So you can't really use the ship while you're generating power to control the gun. And because the current is so high and the temperatures generated are so great that the metal rails degrade very rapidly. So you can't do any kind of repeat rapid fire on these things. So they've not been used yet. A lot of testing. That's Module 9.